Hi there. I'm doing a quick video on determining the striking force of a punch into a punch bag, which is going to involve quite a lot of physics, quite a lot of applied maths, and also a bit of punching. Hopefully we'll be able to, or I'll be able to convince you that maths is actually a very useful tool for working out lots of things that we don't currently know by making various different estimates, assumptions, and using different equations. We're going to be using quite a lot of Newton's laws. We're going to use some energy equations and some Subat equations, some basic equations of motion. Okay, so first thing I'm going to do is hit the punch bag, just because it's fun. Right, so I'm going to strike the punch bag and I'm going to see how far it rises, and hopefully from that I'll be able to work out energy transfer and ultimately work out the power of the punch. So here goes. Okay, now for the maths. We need to figure out the force of the punch impacting the punch bag. So I'm going to use Newton's second law, F equals ma. Okay, so Newton's second law is well known, and it links force with mass and acceleration. So if we can work out the acceleration of the bag and we know the mass of the bag, we should therefore be able to work out the impact force. I'm going to change this up a little bit. I'm going to use acceleration, but instead I'm going to rewrite it from v minus u over t, initial final velocity minus initial velocity divided by time. Time is the impact time of the strike, u is our initial velocity, v is our final velocity. And I can then substitute that in, and we get m v minus u all over t in brackets. And if I expand that out and multiply through by t, I get ft equals mv minus mu. Okay, so you may recognize this. This is called impulse. Impulse is the force times time quantity, and we have on the right hand side mv minus mu, which is our change in momentum. Now, we know that u is equal to 0, which is our initial velocity, so the force time equation or impulse equation simply distills down to ft equals mv. Now, we can hopefully measure the mass of the bag without difficulty. Velocity is going to be a little bit more challenging. Okay, so we need a way of actually finding out the velocity of the bag, or the initial velocity as it's initially struck. And then we also need to consider the impact time, which is actually going to be very short. So I'll deal with that in our next video, but if we can find v and we can find t, we can actually work out the force of the punch. Okay, so we're now going to try and establish what the post-impact velocity of the bag was. Now, the way which we can do this is we need to model the bag as a simple pendulum with mass m, and when an impact happens to one side from the punch, it will be displaced horizontally and vertically based upon an angle which we are looking to measure, theta. So if we draw a horizontal line across, we're looking at the height at which the centre of mass of the bag is raised, and that will give us an indication of how much energy is being transferred, determining the potential energy gained from the increase in height. Now, we can work out what h is, providing we know the length of the pendulum. And we're going to establish the length of the pendulum using, or length of the centre of, from the ceiling to the centre of mass, by using a simple pendulum relationship of the time period. But in the meantime, we're just going to label that L. Okay, so we want to find out the value of h. Well, we know that that's a right angle, and this distance from the line at which it reaches horizontally to the point at which it's fixed, using simple trig, is L cos theta. So I can get h from subtracting L cos theta from L, so it's L minus L cos theta, and then I can factorise 1 minus cos theta. So there's our value of h. Now that's actually helpful because that allows us to start using energies. So we can work out the potential energy gained by the punch bag by using the relationship potential energy PE equals mgh, which we can rewrite mgl 1 minus cos theta. Okay. Now, if we make the assumption that all the energy from the impact is transferred to kinetic energy of the bag, okay, some is going to be lost from deformation and sound. However, we can say that from a simplified point of view, kinetic energy, half mv squared, all turns into potential energy as it rises and stops and reaches its highest point. So we can say that half mv squared equals mg L 1 minus cos theta. Now, you can probably see that m appears on both sides, so this relationship does not depend on mass. So we have a half v squared equals gl 1 minus cos theta. Multiplying through both sides by 2 and then finding the square root, we will get a relationship between variables giving our velocity is equal to the square root of 2gl brackets 1 minus cos theta. Now, we can establish what the length of the pendulum is to the centre of mass. We know that g is approximately 10. The only thing we don't know is theta. Now, when I slowed down the photography, slowed down the film, and I made a ballpark estimate, I established that theta was approximately equal to 30 degrees. Now, this is by no means accurate, but all these things require some simplification and estimation. So it's as close as we're going to get without any sort of really in-depth video footage. However, 30 degrees was a reasonably good estimate, but it will cause some error in our final calculation. Okay, so we're going to move on to the next bit. What I could do is measure the length of the pendulum from the point at which it's fixed, or the punch bag, to somewhere along the middle of the punch bag itself to roughly establish the length of the pendulum. However, this is not the best idea because we don't know if the distribution of mass throughout the punch bag is uniform. So I'm going to be a bit clever about this, and I'm going to use the relationship between time period of a pendulum t and its length L. So what I'm going to do is I'm going to measure the time period of the punch bag by displacing it slightly and working out the total time period of 10 oscillations, and then therefore working out the time period of 1. So here's the boring bit. Off we go. 1, 2, 3, etc. So I'm going to count up to 10 and I'm going to time it. In fact, I've already done this, and when I did so, I actually ended up with the total time period of 25 seconds, making a time period of one swing to be 2.5 seconds. So we're now going to use that, do a little bit of maths, and hopefully we'll be able to figure out the centre of mass of the pendulum, or rather the punch bag. Okay, here we go. Okay, so we've just established the time period for oscillation for our punch bag was approximately 2.5 seconds. Okay, so we can use this to establish using a relationship which you should be familiar with. If not, this is something that comes up regularly in A-level physics and also further maths. Time period of a pendulum is equal to 2 pi multiplied by the square root of L upon G, where G is the acceleration due to gravity, which is approximately 9.8 we're going to use. We'll put some units in, meters per second squared. And L is our length, which is what we're looking for. So we need to rearrange this to get L the subject. So the way to do that is we want to initially get rid of the square root sign. So we're going to square both sides, making sure we square absolutely everything. So 2 squared, pi squared, and then we're going to square root everything under the square root sign, giving us L upon G. Remember, we're looking for L as the subject. Multiply both sides by G, we get GT squared equals 4 pi squared L, and then finally we know that L must be equal to GT squared over 4 pi squared. Okay, so we know some values. Now I'm going to be a little bit kind of I'm going to estimate some things to make our life a little easier. I'm not going to use a calculator. I'm going to say that G is approximately equal to 10. This is something I used to do during my PhD, which was what's called a back of the envelope calculation, estimating everything. Okay, now T squared, I know that T is 2.5. Well, actually, I can say 2.5 is 5 over 2 and square that. Work with fractions, much easier. 25 over 4, which actually is about 6 1/4 or 6.25. So I'm going to call that 6. Okay, let's change that to approximately equal to. Okay, remember all these things are estimates, but it doesn't matter because we are just looking for a ballpark figure here. Okay, so based upon this, L is going to be approximately equal to G, which was 10, times T squared, which is 6, over 4 times, and we're going to say that pi is 3, so we're going to do 4 times 3 squared, which is 4 times 9, which is equal to 60 over 36. Okay, I'm going to simplify that, and I'm going to get 30 over 18, 15 over 9. Oh, I can go even further. Divide by 3, so I get 5/3. Okay, so L is approximately equal to, so what's that? 1 2/3, so it's about 1.6 recurring meters. Okay, so we've now got a value of L for our pendulum. So all we now need to do is plug everything in to all the relationships that we've actually done. I'm going to do that in a summary in a minute. Right, it's time to piece everything together and see where we go. So we know that the velocity is reliant on this relationship, square root of 2gl brackets 1 minus cos theta. So we're going to say that g is approximately equal to 10 meters per second squared, just rounded. We're going to say that L from our pendulum calculation was about 1.67 meters, and from an eyeball approximation, fairly uncertain, but we're going to say that theta was about 30 degrees. Okay, so when we plug everything in, we get an initial post-impact velocity of around 2 meters per second. So we can work with that from our impulse equation, Ft equals mv. Remember, force times time is impulse. Mass of the bag multiplied by the velocity or initial velocity of the bag is its momentum. So we're looking to find F, which was the impact force mv upon t. Now, I made a measurement of the mass using some scales, and it was about 20 kilograms. Our velocity we've established was about 2 meters per second. The problem we have is our impact time. Now, it's going to be very short and very difficult to measure. But what I did do was I slowed down the video footage, and it was running at 60 FPS, and it was clearly evident that there was an impact for approximately 3 frames. Okay, once again, a little uncertain, but we're working with what we've got. So our impact time is approximately 3 frames out of our 60 frames in 1 second, which gives us 1/20th of a second, or 0.05 seconds. Okay, again, cause for error, but it's all we've got to work with. So let's go for it and see what we get. We get the force equals mv, which is 20 times 2 divided by 0.05. Okay, and we're going to end up with roughly an impact force of about 800 newtons. Now, I did a bit of research, and the average untrained person is likely to deliver an impact force of approximately 700 to 800 newtons. So that's an untrained person hitting a bag, possibly for the first time. Now, that might appear I'm a bit of a wimp, or actually I didn't hit it quite as hard as I should have done or could have done, because I didn't want the bag to be all over the place, so I couldn't track its motion. And also, you'll note that a lot of energy is actually deforms the bag and is released as sound. But I think you'll agree that our ballpark figure and the research agree very, very closely. So, with all that estimation, I didn't think we did too bad. Thank you.